Hello, everyone. I hope you guys are doing well. It's been a while since we met last time. I'm sorry I couldn't make it during week 9 due to health issues. I'm getting better, and I decided to continue our classes sadly online because we cannot make it to the class due to the coronavirus. And we're gonna continue from where we stopped last time, and that was mainly on we were talking about conditional processing. So the main idea of the conditional processings, as you can see in the slides right now, please let me know if you don't see the slides, so that way I would understand the quality of my recording, and I promise I will do a better job every time you provide me with a feedback. So you can see in the title right here, we focusing mainly on conditional processing, and we understand the basic idea for the conditional processing. Let me see if I can make this one a little bit better. I'm just learning the technology. Hopefully this is going to be a little bit closer to the board. That's the best I can do. So if we have, as we learned last time, if we have a condition, let's say A is less than 5. So this is mainly what we need to capture, or this is how the CPU is gonna handle this condition. So this is usually an if statement, right? So the CPU needs to figure out this relationship. All right, so it's a hardware as we talked about it last time. So it's mainly hard to decide or hard to figure this relationship out. So one thing the CPU could do is to use basic logical operators like the one we covered in the class, and the one that does not affect the destination register, which is test, right? So these are two type of instructions that they are used to do conditional processing. And we also learned about compare, but we haven't yet covered. And compare relies mainly on subtraction, but we know subtraction is a destructive instruction. Remember, destructive instruction is an instruction that is going to affect the destination register. So compare is going to be a subtraction without affecting the destination register. Okay, so this is what we did last time. These are the instructions that we looked at. So the whole idea is to do conditional processing as we covered in the class. And we looked at the AND, OR, XOR, and NOT, and test instructions. And today we're gonna cover compare, and hopefully we're gonna move into the if statement, because the whole idea of applying those instructions is to handle the if statements conditions. We need to understand how a CPU handles conditions, right? So we covered all of that. We know how the E flag is important for this particular task. So the instructions right here, if you remember the bird analogy, so we need an instruction right here, an operation or instruction that's going to affect the E flag, which is the register, right? And mainly it's the arithmetic E flag registers. And we need another instructions that's going to make the decision. That's read the register and make the decision. So for this instruction, it's mainly the AND, test, and compare. These are the ones that they're going to do the effect. They're going to affect, or they're going to trigger a specific values on the register, like this, like the sign flag, like the 0 flag, okay? So, and so on and so forth. Carry flag, overflow flag, okay? And then once this instruction does that, then, or did that, then there must be a J, if you remember, a J instructions that's gonna go and read the value, and based on that is gonna make the decision, because you know in an if statement, it's a branching. That's what I mean by the B, if you can see it in the board. So we're gonna either go with the true. If it's true, we are not jumping, we're executing the statements, and then we're gonna continue the sequence or the rest of the program, or we're gonna go to the false part, and that's in the false part, we're gonna go jump over the if then statement, and we go to the next part, and that is going to be accomplished with the help of these two instructions, okay, which is the instruction that affects the flag and instruction that's going to read the flag and make the decision. All right, so these are all things that we covered. These are the flags you guys are familiar with, and this is how the AND works, right? And this is something we played with in the class, and especially if you look at this example, let me see if I can annotate that. I'm sorry, I'm just still learning the technology. So if you remember last time, when we played with this part right here, and especially the AND, we saw how AND affects the register. And in this case, we're gonna AND 80 with one F, right? So if you break this one down, let me see what I can do. If you can break this one down, just to remind you to see the effect of and J, because this is the way the conditions are handling by the CPU. So that's what we did in the last time. So we know that this is 8, and we know that that is the 0, right? And then we have the 1. So this is the 1 in binary, and this is the F in binary, right? And we need to and, not add, and them together, right? So we can tell that everything here is going to be 0 because we don't have 1 and 1, right? So if that is the case, then and is going to do this and is going to inform the E flag. So in the E flag, we're going to say the Z flag is now equal to what? Is equal to 1. So then now we have the J instruction. So that's the first part of the bird, right? This is the first part of the whole operation. And it just said, I'm done. I did what I supposed to do. Then the J, we say J based on a specific condition, which is right here, jump when it is 0. That means jump when the 0 flag is set. And the 0 flag right here is set. That means we're going to go to whatever the label you have right here. So this is just a label, right? So if this label right here says to do set of instructions or one instruction, we're going to go there and do it. So that is the whole idea. Okay. So let me move on now to the next, if I can. Let me just see how I can get rid of this one. So we're going to say clear this part. So clear my old drawing. Okay. And let me see if I can move on now. Okay. You go away. All right. And then that's what the end is. This is another example that we both discussed. We discussed in the class, and this is how OR works, though we did not use OR in this, in our class, but it's always good to know how the bit manipulation works anyway. Okay, and then we played with the OR, the flags, and how OR works, and this is all done during the on-campus classes, and we did the XOR and the application of the XOR, and we did the test, and we saw the difference between and the test. So the whole idea is the same thing. Test is not gonna destroy the value. So if you do and in here, if this value right here, the destination, is stored in the register AL, then now the AL is no longer 80, it's 0. So and is going to destroy the value. But when we do conditional processing, we don't really care about the content. That's going to take us more time to go and update the value. So instead of using and, we can use what? Test. So the test is going to do the same, but it's going to keep the value as is, because it's the whole idea just to affect the flags. And I hope that was very clear in the class. If it's not, please leave your questions on the discussion section. I will create a discussion section for the video, just in case if you have some questions. I will try my best to go there, and if the time allows, and just to reply to your questions. All right. So this is how the tests work, and the compare. This is where this is the thing that I remember I covered for one section, but not for the other. Okay, so right here, what we're gonna do, we're gonna focus on the compare. So the whole idea remains the same, guys. So the whole idea right here, we're gonna look at the compare the way we learned and. So we don't use and heavily when we do real assembly programming. We heavily use compare. And that is maybe for one obvious reason, right? Because the arithmetic, if you look at the E flag, the way the comparison happens is if you have is a equal to 5 and a less than 0, right? So how the CPU is going to decide this? So the main idea is to do subtraction, right? If you subtract 0 from 5, then you're going to get the result 5, right? So if this result is 5, that's going to trigger what? The sign flag, the 0 flag, the overflow flag, the carry flag, right, guys? And based on those flags, we're going to do some comparisons, right? We're going to make some decisions. So the whole idea right here is the subtraction. So the CPU, the way the CPU really make difficult decision is not by using and. And is going to solve simple problems. So that's why we're going to focus mainly on the compare, because it's subtraction. We solve comparisons, most of the comparisons are relationships using the subtractions. So compare is subtraction. So it's mainly, if you look at it, if this is something you still remember, the thing that we covered in the class. So the compare is just going to be basically subtraction, but it's not going to destroy. So it's an implied subtraction. So it's not going to destroy the value and the destination value and the destination register. So it's non-destructive subtraction. So we don't care much about the mechanics right here. All we care about is the big picture, the whole idea that the J instruction needs to make a decision. And that is only possible if another instruction before that, like compare or and, is going to affect the flags. Okay, so this is the destination and the source, and it's not going to change anything. And these are the flags. It's going to affect overflow, sign, 0, carry, and so on, and the rest of the flags. So we're going to focus mainly on the sign, 0, and this class, sign and 0 flags. All right, so this is the way compare works. So if you want to know whether the destination, let me see right here. Again, I can use the notation. So if you can see right here, if you want to know whether the destination less than the source, this is something very easy. So you just do the subtraction and look at the value of the sign flag and the overflow flag. These are the sign flag and the overflow flag. If they have different values, they are not equal, then we know the destination is less than the source, right? So for that to make sense, let's just look at a very simple example. Let's say we have an A right here equal to 5, and let's say we're going to compare if A less than, if A, let's say, let's make A 15, okay? And let's say if A less than 20, okay? So we want to know that the destination less than the source. So here, destination is less than the source. In our mind, biologically, we've been trained, right, to do these basic math, right? But if you want to create a machine that's going to make similar decisions, then you need to train them. So this is exactly how it works, right? So you're going to look at this A, so you're going to say 15, and you're going to take out of 15 what? 20, right? So you're going to have a negative 5. So the sign flag here is equal to 1, and the 0 flag, hopefully you guys see this, and the 0 flag is equal to what? 0. So sign flag is 1, 0 flag is 0, and as you can see right here, so the sign flag is not equal to the 0 flag, right? So if that is the case, then we know that the CPU is gonna decide that the destination is less than the source. Okay, let me get this one a little bit closer. Hopefully this is gonna make things better. Okay, is that kind of clear? So this is what we did last time. And the same applies for the destination and the source. If you want to know whether this is greater than, if you want to play with this value again, as I said in the class, you're just going to say this is 50. All right, so if you want to do this for the 50, we're just going to look at the same thing. We're going to use compare, which is nothing but subtraction. And then we're going to compare sign flag with the overflow flag. Okay, so if we want to do this one right here, then we're going to subtract from 50, 20, and that's going to give us 30. So we care about the status, remember. We don't care about the value because compare is not going to store this value back in A. So the status is positive. That means the sign flag is 0. And the result is not 0, then the 0 flag is 0. So both of them, they are equal, right? So the sign flag is equal to the 0 flag. If the sign flag is equal to the 0 flag, that means the CPU will know that the destination is greater than the source, and that makes sense. 50 is not less than 20, right? So, or if you want to look at it right here, if you want to look at the true part of it, you're just going to change this into greater than. So that makes sense. That's true. If you want to know, if you want to know how the CPU is going to decide this particular problem when it is a equal to, so this is, let's say this is 20, just for the sake of simplicity. You can play with whatever the example you feel makes sense to you. So again, the CPU is going to subtract. So we have a as a 20, and we subtract this 20 from it, right? So this is going to be a 0. So if that is the case, as you can see right here, the 0 flag is going to be 1, and the sign flag is going to be 0. So we know here that the 0 flag is 1. We don't care about the sign flag right here. If it's for doing conditional processing for equality, we care much about whether the 0 flag is 1. If the 0 flag is 1, then we know that the destination is equal to the source, and that is what's the case. And in this example, what the case is in this example. All right, but you need to really understand that compare handles sign and unsigned differently. So this is something very important, and I hope that you already looked at that in the previous slide, right? So if you look at that in the previous slide, let me see if I can go back. Okay, you go away. Okay, so in the previous slide here, if you look at the title right there, that is the title. So it's unsigned. So if it's unsigned, we only have 0 flag and carry flag. And you already should have noticed in this case, if the destination less than the source right here, when it's unsigned, we don't have the sign flag because this is all about unsigned, right? This is unsigned integer processing or unsigned conditional processing. So if you can see, if the Z flag is 0 and the carry flag is 1, then the CPU is going to say, I'm out. This is a negative number. And if you mean that this is an unsigned number, I don't see it that way. So I don't care. I will consider it sign, and then I will move on. So you're going to have a problem. I will try to show an example using the Visual Studio. I just have a hard time capturing the Visual Studio using Zoom. So once I do that, I will start to heavily use Visual Studio and show you live examples, all right? But you need to understand that compare completely see things differently when it is signed or unsigned, all right? Okay, so hopefully things are very much clear so far right here. So that's what we're gonna do. And then this is what the case is. If you look at this example right here, if you wanna compare AL with 5, and you're gonna look at this table. So this is just a couple of examples for you to play with. So in this example, as you can see, that we have moved 5 to an AL, and we compared 5 with 5. So we know how the compare works, right? So it's going to subtract 5 from 5, right? And the result is going to be what? Is going to be 0, right? So if that is the case, then is the destination less than the source, or the destination is equal to the source? So if you look at the case that we have right here, so we know that, let me see again. I want to get this guy out. Yep. So if you see it right here, so the Z flag right here is going to be 1, right? And the sign flag is going to remain the same. In this case, it's 0, or the carry flag is going to remain the same because you are dealing with the unsigned, right? So if that is the case, then we know that the destination is equal to the source. We know, I'm referring to the CPU. So the CPU knows that the destination is equal to the source. And based on that, the G instruction is going to come and make the decision. So this is only affecting the E flag. And then the compare said, I'm out. Then the J instruction, the J instruction is going to come and make the decision. Okay, so let me see right here. So I will move to the other example. So right here, we are comparing 4 to 5. So we are subtracting 5 from 4. It's not destructive. So it's not going to destroy the value in the destination, just going to affect the E flag. And the E flags that we are focusing on right here is the Z flag, and it is the carry flag. So if you subtract this from this, you're going to have what now right here? -1. And remember, you're dealing with the unsigned. So if the sign flag right here, that is the 0 flag, right? So the 0 flag is going to be what? It is going to be 0. And the carry flag, this is going to be 1. Why the carry flag is 1? So if you think about it, we are dealing with unsigned. And if the result is negative, that's going to trigger the flag because it says, you did something I don't really understand anymore. So I'm raising the flag. I'm no longer handling unsigned. You say handle unsigned and you change your mind. So if that's the case, then we have 0 and 1, and you can see this in the table. If it's 0 and 1, we know the destination is less than the source, and that makes sense. 4 is less than 5. So this is how the microprocessor is gonna decide which one is what. And that's it, they're gonna get out. So that's happen with the help of compare. So now we need a J instruction. So in this case, you might jump when 0 flag or maybe when carry. You can say jump when the carry flag. You can say jump when it is 0. So it depends on the way you're gonna make the decision. So that is very important. And we understand that when we jump, we're talking about the dot code memory. And in the dot code memory, you have set of instructions, right? That's what your program is, right? So this is instruction 1, instruction 2, and we have instruction N, right? So maybe if this is true, you're going to execute the instruction and you move on. If it's false, you need to jump over. And when we say we jump over, you are moving inside the dot code space, not the dot data space, right? So I believe that this is something clear at this time, okay? And these are just like more examples. Try to look at them and play with them and let me know if you have any problem, okay? I will leave that up to you. All right, so the same applies for the 64-bit programs. So if you want to do this for the 64-bit programs, this is going to help you as well. So I will leave that for right now because we are just covering 32-bit, but just look at this slide in case in the future you want to use the 64-bit. All right, so now we want to go to the conditional jumps, right? So that's what we talked about right now, which is the J instructions. Okay, I'm sometimes confusing you. I say G, J, G, so you know what I'm talking about, right? So if that is the case, then that is the whole idea of this chapter, is to understand how conditions are processed. Okay, so we need to know it is compare and J. You can use and, of course, but regardless, you need an instruction to affect the flags and instructions to read from the flag and make the decision. And that is exactly what I'm trying to do right here. Okay. So I will try to talk about these instructions. So these are the mnemonics, the instructions right here. If you want to make decision based on a specific flags, you can do that, and that's common. Okay, so you're going to jump when it's 0, not 0, jump when it's carry, jump when it's overflow, and so on and so forth. Or you can choose from equality, because we understand that x86 is a CISC architecture, right? CISC means what? Complex. Right? It has more instructions than the ARM, which is RISC, reduced instructions. So if you don't like jump with 0, jump with overflow, you can use things similar to the high level, right? When we say less than, greater than, or equal, you have them here. Jump when it's equal, not equal, jump when it's the register CX is equal to 0 or not, and CX could be 16-bit, and it could be right here 8-bit, 16-bit, and 32-bit, and 64-bit, okay? Or you can make them based on unsigned or signed. Are you handling signed or unsigned? You want to be very sure about what you are doing, right? So one thing that, if you can see it in the bottom right here, let me see if I can use the annotation, though it's not very flexible, but there you go. So in the annotation right here, if you see A, small a, or capital A, it doesn't matter. If you see them there, okay, that means you are dealing with the unsigned. So if I see in the exam or in the test, you say jump when it's above, or jump when it is below. So that tells you, without me telling you what the value is, you will go with the assumption that the value is unsigned, okay? So these instructions, jump when it's above, below, below not equal, below, and above or not equal, these are the instructions that we're gonna use heavily, and they make a lot of sense, okay? So we're gonna move to the sign comparison right here. Let me again see if I can clear that diagram. Now we can look at some other jump instructions using sign, when the value that we are comparing, or the values that we are comparing, are signed. Okay, if they are signed integers, then we have to think about G or L. Okay, so if you want to see that, let me see what I can do. I think I lost the ability to browse, but let me see. Yeah, close it. Give me 1 minute, guys, please. So I'm trying to just move on to the next instruction, but for some reason, okay. Okay. So back to here. So here, if you look at it, if you are dealing with instruction that they have jump if it's J, or jump if it is greater, G, or less than, then you're dealing with the sign numbers. Okay. So you can do this. And right now we are ready to go and look at the applications. So we're going to look at how these are going to be applied, and then we're going to look at how to do this for when we deal with the F statement. Okay, so let's just look at some of the applications for the remember, A and B for unsigned, and J and L for the sign. So if you see them written in this way, compare AL with 5 and jump when it's above. So you're going to assume what? What is the value in AL? Just assume if you move to AL 5. So what you assume 5 to be, it's going to be unsigned. So you don't care about it, okay, if it's signed. So that's how the CPU is gonna process that value. It's gonna consider the context of that value. Okay. So if you look at some examples here, they are straightforward. You want to compare AL with BL, and you're going to jump if it's above. So without even me saying it right here, if you can see it in the red color right there, without even me saying unsigned, you know that you're dealing with the unsigned number. What happens if I assign a negative number? So let's say, if just for the sake of simplicity, what if you have a negative number? Let's say this is a simple negative number, right, guys? This is -7, right? So if you give this -7 and you're trying to compare -7 that it is going to be greater than 0, right? So if you want to do this, should be a true or false condition. So if you look at it, this is not greater than, this should be false. But if you are dealing with the unsigned, this -7 here, it's going to be seen as what? 9. So 9 is greater than 0, so the CPU is going to consider this one true. You or we, as a human, in our mind, we think that this is false because we thought -7 is signed, but the CPU is going to say, hey, you already use what? You already use jump when it's above. So you already said compare AL, which is -7, with 0, and you tell the CPU to say jump to the label if it is above. So if it's above, it says, I don't care about the sign, the most significant bit, so I would just gonna consider this value as just as 9, which is positive value. So the same applies right here. Okay, so this is simply what the case is. So you're going to see at the example right here when it's for the above, and right here for greater. So you know that you're dealing with a sign. And these are like more examples. All right, so please play with those using your Visual Studio at home. So these are different applications. All right, so these are multiple examples right here. So one thing that I need to point out right here is right there, you can compare a memory, and we know what type of access memory mode is this, right? So we're accessing a memory of size 2 bytes, right? Right, guys? And using the PTR, that is the operator, and that's exactly where the address is. So that's the ESI is the address of where that value is. So the whole idea of this statement, if you feel like you forgot, since it's been a while now, so you are actually saying, I have a value. Let's say memory variable name is A, and I have 10 in here. And we know using the offset, we're going to store the address that represents A inside ESI. So in other words, this is indirect way to accessing the memory, right? Instead of saying A, we're saying ESI, just in case if you forgot. Just go back and try to look at chapter 4. All right. This is a very interesting example right here. I would like just to focus on this part. Here, if you want to do jump to the label L, if the bit position, location, 0, 1, and 3, and all are all set. Okay, if that's the case, we want you to jump. Okay, so to compare the result with what? So let's say whatever the value is, you have a value stored in a register, a byte register. And we know that if we have it stored in the byte register right here, right? This is what the byte is, 1, 2, 3, 4, 5, 6, 7, 8, right? So we are focusing on 0, 1, not 2, and 3. These are the ones that we want to know. And if they are set right here, that means if they have ones, then we want to jump. We don't care about those. These are question mark. Okay, so if that is the case, then we're just gonna ignore it. So this is exactly what the example is all about. So you're gonna end the value in AL. You can assign any value, just assign 5 to AL. And if you assign 5, that's gonna be 1, 0, 1, 0, 0, 0, 0, 0, right, guys? Okay, so of course I forgot, I confused you. We know that the bits are gonna be counted from here, right? So this is 0, 1, 2, 3. I'm sorry, it's my fault. I just used English instead of CPU. So this is gonna be 0, 4, and so on. So we're focusing on bit number 0, number 1, and number 3. So if you assign 5, this is 1, 0, 1, right? And then 0, 0, 0, 0, 0. If you end this value with the value given to you right here, which is 1, 1, right? 0, 1, and then the rest is going to be 0, 0, 0, 0. Why we did this value? This is what you call the mask. Because we want to end. We know if we end and we have a 1 right here, we're going to get a 1 right here. And we care about bit 0, 1, and 3. That's why we put zeros in there. So here it's going to work. It's going to be 1 and a 1, but here it's not going to work. Okay, so when we do this ending, it is not going to show jump when it's equal. So it is not equal. So we are not going to jump to the label. All right. So I'll stop right here, take some break, and then I'll go back and talk about the conditional processing. Okay, guys. So as I said again, just keep your eyes on the iCollege, and please try to watch the video and let me know if you have any questions. All right. Okay, then. See you later. Thank you.